Good morning. My name is Nomfundeso Mkize. I'm a student at University of Technology. I'll be taking you through my assignment for ETM 4801. So in the introduction, today we'll be embarking on this journey. We will discover the indispensable role of electromagnetic waves, particularly light, in modern communication systems. So from the wave-particle duality of light to the emergence of fiber optics and the incorporation of electricity in powering these systems. So our aim is actually to unravel the profound relationships between these two domains. Firstly, on our first slide, we have basic of optics. We have the first one is light as an electromagnetic wave, wavelength and frequency, reflection and refraction, we have diffraction and interference, and polarization. With light as an electromagnetic wave, light is actually a form of electromagnetic radiation. It is characterized by the electric and magnetic field that oscillates in harmony. With the wavelength and frequency, that's where light waves, they are characterized by the wavelength and frequency. And with reflection and refraction, when the light encounters a boundary between two different materials, it can reflect or refract, meaning that it can bend. A reflection occurs when the light bounces off a surface, for an example, like a mirror. So refraction occurs when a light changes direction as it passes from one medium to another. With diffraction and interference, light waves can diffract, which means that they bend around the opticals and spread out as they pass through the narrow opening. With the polarization, that's when the light wave, we know that the light waves can vibrate in different direction, and their polarization state describes the orientation of these. So polarization is very important in the optical systems. On our second slide, we have electromagnetic spectrum. We can see we have a picture there which shows our spectrum from radio waves to microwave to infrared to visible light to UV, which is ultraviolet, to X-rays, up to gamma rays. With our radio, we have 10 to exponent 3, as you can see there. Microwave, with the radio, 10 to exponent 3. Microwave, 10 to exponent minus 2. Infrared, it's 10 to exponent minus 5. Visible, 10 to exponent minus 6. Up to gamma rays, which is up to 10 to exponent minus 12. It also have different colors. We can see also there the frequency that I just explained, temperature, everything is there on that picture. And then as we move to the next slide, our next slide is light as an electromagnetic waves. So we have on this slide we are defining what is an electromagnetic wave. So these are composed of oscillating electric and magnetic fields, and then these fields are perpendicular to each other and they propagate through space. And then the characteristics of light waves, we name transverse nature, we name wavelength, we name frequency. We know that frequency refers to the number of oscillations per units of time. So it is measured in hertz. And then wavelength, there is the distance between the successive wave crest. So in the case of light, it is typically measured in nanometers. And then we have transverse nature. Light waves are transverse, meaning that the oscillation of the electric and magnetic field are perpendicular to the direction of the wave propagation. On the next slide, we have wave-particle duality. So wave-particle duality refers to the fundamental property of matter, where at one moment it appears like a wave, yet another moment it appears like a particle. So on this slide we have we are differentiating particle and waves. So with the particles, we know that light behave as if it's composed of discrete pockets of energy called photons. And then each photon carries a specific amount of energy that is directly proportional to the frequency of the associated wave. So this relationship is described by Planck constant, which is E is equal to H multiplied by F frequency, where E represents the energy and H represents the Planck. And then on the other hand, we have waves. In some experiments, light exhibits behavior consistent with that of a wave. So this includes the phenomena like interference and diffraction, which are characteristics of wave pattern. Interference occurs when two or more waves overlap and combine, leading to either reinforcement or cancellation. So diffraction here is the bending of a wave around the obstacles and occurs when a wave encountered aperture or obstacles that is of the same order of magnitude as it is of wavelength. And on the next slide, we have fiber optics. Fiber optics are actually technology that uses thin, flexible, transparent fiber that are made of glass. We all know that fiber is made of glass or plastic. It's transparent. So the advantages of fiber optics: the first one, it has a very high bandwidth, so it can carry a lot of amount of data due to the high frequency of light that it have. And then it also have a low signal loss, meaning that it can travel over a long distance with a minimum loss. And then also another advantage is immunity to electromagnetic interference. Fiber optics are not only affected by the electromagnetic field, making them secure and reliable. And then the applications on the fiber optic: the first one is telecommunication network, the second one data carriers, the third one medical imaging, and the fourth one is military and aerospace. And then the basics of the optical fiber: the first one is the structure, and the second one is the total internal reflection. It is called TIR. So the structure is it consists of several components. The first one is the core. And we have a cladding, we have a buffer coating, and we have a jacket. So all these are covering our fiber. It's protecting our fiber, And then on the TIR side, the total internal reflection is a critical principle that allows optical fibers to guide light effectively. When the light is traveling within the core, strikes the core cladding boundary at an angle greater than the critical angle. It reflects into the core instead of escaping. So this phenomenon ensures that the light stays combined within the core and travels a long length of the fiber. On the next slide, we have electricity in optical communication. We have the symbolosis of electricity and light, key electrical components. We have laser diodes, we have photodetectors. Under photodetectors, we are talking more of photodiodes, photoresistors. So these are the receiving ends of optical communication in the systems. And then on the next slide, we have the magnets and optical communication. The first one is the symbiosis of electricity and light, key electrical components, laser diode, photodetector, signal processing, and power supply and control. On the application side, as we all know that we are moving to the new normal, so now we have the real world applications that where this fiber is being used. So it's actually used in telecommunication networks, it's used in data centers, it's used as a internet backbone, cable television, military, aerospace, medical, imaging, and imaging technologies. Like there are many more other applications. And then our recent advancement, we have quantum communication. These systems are designed to operate in conjunction with the traditional optimal communication. We have photonic integrated circuits, we have high capacity optical transmission, we have wavelength division multiplexing, which is WDM, we have space-based optical communication, and also machine learning for network optimization. And then challenges and the future prospects are on the slide. Challenges that include signal loss and dispersion, security, network scalability, energy efficient. And our future prospects include 5G and beyond to 10G. It include quantum communication, green optical network, IoT, Internet of Things, and space-based communication. Those are our future prospect. And then in conclusion, we know that the relationship between electricity and magnetism is at the heart of optical communication, revolutionization, and the way we connect, we communicate, and innovate. And here on our last slide, we have our references. If we want to go back and read more, these are the references. That is where we got all the information that is on this presentation. Thank you.